Alright, and we're back again, continuing the development of this Linux air combat program. Yesterday when I left off, I was adding this, what was it? Conan support to the CMake build files. That was incredibly dull and also incredibly painful because everything involving CMake is painful. But I have that figured out now, so we can actually continue going. I can look at some of these CMake files to actually see what I changed. So, once we actually have Conan installed, the changes to the CMake file are pretty simple, and then we can just include the Conan, we can just add the Conan include directories and the Conan libraries, and then it all adds into our build system. So that's painful. But we have all that working now, so we can just close all these tabs. We're going to continue developing on the model viewer. So what we have yesterday was creating this window and the very basic event loop. And we're going to continue to add a OpenGL renderer to this. So actually, one of the first steps I need is now adding a new Conan package. I'm going to be using this OpenGL loader library called GLAD, which should be a fairly simple way to add OpenGL to our program. There was already OpenGL functionality in the program, but it was OpenGL like immediate mode 1.0, which is very simple to access, but it's the older version of OpenGL, which I don't want to use. To use the more modern version of OpenGL, we have to use a loader library like GLAD, which is what I'm going to add right now. So, not the Conan file. Once we have that, we should be able to actually include GLAD in here and use that to load the OpenGL functions. We also need to make this window make current. So we have to make the OpenGL context current. So the actual function we need to use from the GLAD library is GLAD load GL loader, and we pass it the SDL GL get proc address. So SDL provides the function that allows you to load individual function pointers of OpenGL, and we just pass this function pass this function to the GLAD loader, which then handles the rest for us. So we need to check whether or not this function fails. And if it fails, we just terminate the program immediately. So if we have this, it should just go to our simple event loop and do nothing because all we've done is load the OpenGL functions. But this verifies that we are loading them correctly because it does not hit the failure. Okay. Now that we have that, I change the condition of that. Okay, we should be able to actually call OpenGL functions directly now. I'm just going to call GL viewport, which is a very simple OpenGL function, and see if that actually works at runtime. And it appears it does. Okay, so that means that we have added GLAD to our program. I guess we'll commit that. Okay, so then there's a bunch of like SDL windowing functions that we need to handle in order to um, like alter the OpenGL context. So for example, I was using GL viewport earlier, but that should generally only be called whenever the window resizes in order to match the new size of the window. So we can actually listen to that with this SDL event loop. No, I haven't actually used SDL in a long time, so I don't remember the exact functions. And we need to actually extract size from the active window. So we need to add new functions to the window class. Okay, I don't know why Visual Studio does not recognize this file. That's kind of annoying. Now it just leaves all these squiggly lines all over the screen, but I think we can just ignore that. Okay, so we set a breakpoint inside of this event listener, so we should actually hit that if we resize the window. You know what? I need to mark the window as resizable. I wasn't able to actually change the size there because I didn't set some kind of flag earlier. Yeah, we need to add this function to the window as well. find it kind of annoying that they use this type def enum instead of just a Boolean value. But that's how old C libraries work. They always just find some way to annoy you. Okay, I should be able to resize the window now. Sorry, I need to call that function first. There we go. Okay, so I can resize the window, but it's not actually hitting this breakpoint for some reason. Okay, I don't know what's causing that. That should be hitting the breakpoint. Kind of annoying, actually. Okay, so apparently there are two separate SDL function or SDL events for basically the same thing. I find that to be rather confusing. It should be resized if it's an external event. I was using size changed. Okay, it still isn't working. Oh, I need to actually check this. Okay, there's like nested event types. You gotta be kidding me. Oh, okay, so it only pauses when you release the resizing handle. Okay. Yeah, I'm used to GLFW, which sends it continuously every single time you move like a single pixel. But SDL actually handles this a little nicer. Yeah, so only when I release the resize handle, that's when it sends the event. Okay, so that's how you actually handle window events in SDO. I do want to eventually add multiple rendering backends. So I'm using OpenGL right now. Linux Air Combat says that it runs on platforms like the Raspberry Pi. So to add Raspberry Pi support, we need to actually add not OpenGL, but OpenGL ES, which is OpenGL for embedded systems. That's the actual graphics API that the Raspberry Pi uses. So that is obviously similar, but still a separate library than regular OpenGL, which means we need to have two separate rendering backends in order to support these two platforms. So yeah, eventually one of my goals is to make this support both Windows, Linux, and Raspberry Pi. So probably Raspberry Pi running Raspbian or something like that. And I actually need to go out and buy a Raspberry Pi because I don't have one. But that will be like the ultimate test of this project, is making it run on all three platforms. So anyways, that means that we need to create like a rendering system that allows us to switch out the rendering backend. And I don't want to put rendering code like GL viewport calls directly inside the window function, because that will make it like tightly bound to a single rendering API. So to like abstract the rendering backends, we need to add extra classes that will be like somewhat virtual call based, but still should be fairly performant. So I'm just gonna add a new class called render backend. Okay, so this is going to be an abstract class. And pretty much everything on it is going to be a virtual function. So then we need to make the backing class for this as well. And for right now, the only concrete class we're basing off of this is going to be OpenGL backend. Oh, we need to add 0 here to make that an abstract virtual function. Okay, so that's the header for the OpenGL backend, which we now need to implement. Boy, there's a lot of boilerplate. You need to write a C++ class. And of course, the Visual Studio wants to add all these files to the CMake file. That's not very helpful. I don't know how to disable that, and I don't really care enough to try either. Okay, now that we have this function, this should be defined. And since this is a OpenGL specific file, we can actually include GLAD in here as well. That gives us access to the OpenGL files. And now we can actually instantiate this class. And we should be able to hit this breakpoint, which we do whenever you start the program. So that's from the initial call to backend right here. We continue the program and we can, oh, that's not good. Oh yeah, that failed because I put that before the OpenGL renderer. Or before the OpenGL loader. So I need to do that after the OpenGL loader. There we go. So we have this window that now moves. When we resize it, we hit this set window size again. So we are hitting this function correctly, and that allows us to resize the window later on. So now we can just commit that to Git. Okay, so that means we have this OpenGL backend class, and we need to start adding functions here to allow us to do stuff like loading models, loading textures, and so on to our render backend, which we then implement via our OpenGL backend. So that means we need to add functions that are aware of stuff like the model, mesh, and material class. Oh, Homie D Clown in chat asked, I downloaded your dungeon generator, but how do I get the player to start off in it? The dungeon generator code that I added on GitHub does not really have any support for a player. So all it contains is the dungeon generation algorithm. You're going to have to add player support yourself. I put in the video a sample scene where I had a player walking around. That's not included. That's not included in the GitHub. Okay, so for the mesh loader, yeah, I wrote the stubs for this yesterday. We need to actually load mesh data from the CPU into CPU RAM, and then from there, our OpenGL backend will load this into the GPU RAM. So this is basically going to bridge the gap between, well, we're going to have to use the existing model loader code we have right now because the only 3D models we have are 3ds files. That means we do need to eventually move a bunch of this stuff to, well, actually, let's skip that for now and just like do very basic 3D models like a cube. We just define that in code and then render that to the screen. That'd be a lot easier than setting up, than porting all of this 3D model code. So that means we need to add actual classes here to allow us to create the 3D model data. Okay, yeah, so inside this class, I have this void pointer, which points to local data. That's going to be CPU data that we store temporarily or possibly permanently in this Vertex data class. For most models, this data will be loaded to the GPU and then it can be deleted. But for a lot of models, or for some models, we need to keep the mesh inside memory so we can modify it. At least that's how it works in a lot of game engines, and like that's how stuff like Minecraft allows you to modify meshes at runtime by uh, keeping copies of the mesh data in CPU memory. But for most models, once you've loaded the mesh data to the GPU, you can actually delete the CPU side memory because it only needs to exist on the GPU from that point onwards. So potentially there's going to be CPU data here of a certain unknown size. And we need to add ways to actually define the CPU data directly. Okay, so this load data function is basically going to be like a mem copy. So we need to pass the size of the data and the data itself. Don't know why that's marked as an error. I think it's just Visual Studio being dumb. Okay, so what's the actual format that I want to store the data in? I have it as a void pointer, so that would be compatible with something like malloc, but potentially we could use something like a actual std vector instead of this. I'm trying to think of what downsides there would be to just using a vector. That would actually make this a lot simpler. In fact, let's just do that because I don't want to write the actual like malloc code. So we're going to just store a vector of character data here. Okay, yeah, we're going to have a local data function that's going to, or we're renaming this to load local data instead of just load data. And that's only going to, if the size of the local data vector is greater than 0, that means we have data loaded. Again, I don't know why this is showing as an error. Oh, I did not name the class, or I put the wrong class there, that's why. There we go, that should be correct. And then we can do the actual mem copy once we, well, okay, we call reserve to make sure the local data is the correct size, and then we can call the mem copy function to fill the local data buffer. Okay, so once we have that, we can actually fill that with some test data in the main function for right now. So we have engine mesh. And the actual function we just wrote was for the vertex data. So we fill out these parameters, mesh data. We're going to be describing the position of the mesh data. And the format we're using is float32 vec3. And we need to add a function to the mesh class to allow us to add that vertex data. Actually, I think these should be shared pointers. Which means I need to add that the memory include. Then we can define this function on the mesh class. Okay, so we create the shared pointer that stores our vertex data, and then we simply add the vertex data to the mesh. And that should work with no actual effect yet. Now we got a linker error here. Oh, you know what? I did not define the constructor for this class. Okay, so this still has no effect because we haven't actually loaded any data into the mesh, and we're not rendering the mesh. And this is the first step towards loading data onto the GPU. So to actually define the vertex data, at least in code, we need a type that represents float32 vec3, which we could write that type ourselves, but at this point I want to add another library as a dependency, which is GLM, the GL mathematics library. So we go to the Conan file again, look up the GLM library, which is right here. And we can add this to our code base. Okay, so we have GLM included here. We should be able to define actual GLM types now, like GLM vec3. So that allows us to define individual positions within this mesh, individual vertex positions within the mesh. So if we want to define a cube, we need to add at least 8 vertices, potentially more, because we're... Okay, let's start with less than a cube, but just a square. So we want to do, this is in, the first vertex is going to be 0, 0, 0. And we want the next one to be 0, 1, 0. And so on until we can define the 4 points of a square. And that allows us to load the vertex data into the vertex. It allows us to load the vertex data into the vertex data class and then add that to the mesh. Actually, it's not even because to draw a square we actually need to do stuff like index buffers, but I want to stick to just a triangle for now. So there's only going to be 3 data points here. And if we run this, we can actually inspect to see, oh, never mind. Okay, I don't understand what that error means. Okay, I can't say I've ever had this error when using a shared pointer before. I must have defined this incorrectly because I don't understand where this error is coming from. Vertex data is a shared pointer of vertex data type. Calling it would make shared. Oh, I give these the same name, that's why. Okay, yeah, C++ allows you to shadow variables. It was a fun source of bugs there. Okay, so that's compiling correctly. Now we can run it and inspect the vertex data to see that we have the local data is empty still. Oh, you know why? Instead of reserve, I need to call resize. Yeah, there we go. We have size 16, and this contains all 0 bytes. That should not be all 0 bytes. There should be actual data in there. Yeah, there should be actual data loaded here at this address. Oh, I need to update this as well. Yeah, size should not have been 16. That's too small for the data we're giving it. The actual size is 36. That should give us a size of 36 in the buffer. Yeah, there we go. We're starting to get actual vertex data here. So this is a floating point data, but we're just looking at it as individual characters. So this is nonsensical data, but it's non-zero. So that means we're loading the data correctly. Okay, so that means our mesh now contains one vertex data stream. Need a way to expose vertex data. and then a way to get individual vertex data elements. Also, we need to make sure that null pointers are not submitted to this mesh. And now that we have the mesh data loaded into the mesh class, we can actually write the load mesh function. So I haven't actually written OpenGL in a while, so I don't remember the exact way to load models. This is more or less following the OpenGL tutorial because that's the simplest way to write this. But yeah, we need to create the buffer index, which is just an unsigned int, and called gen buffers. Okay, so I was just thinking we need to actually store the mesh ID somewhere, and the most logical place to store would be inside the mesh class. But I don't want any OpenGL specific code to be in this class. So we need to actually add another, like a void pointer here. So m render data. And this can store OpenGL specific data inside the mesh without it actually, without the mesh class knowing about the specific data. So I think we need to start adding some helper classes here, or some storage classes. Yeah, I'm trying to think that a void pointer isn't really the best, like most obvious solution here. Something like a unique pointer would be better, but a unique pointer of type void is not actually legal in C++. So I'm wondering how this field should actually be defined. I really don't want to do a shared pointer, but I also don't want to do new delete. Okay, I know there is actually a way to do a void unique pointer, but it requires like more template arguments. And the problem is it requires a lambda or a well, this one is defined using a lambda, but that's not a very good way to handle that. No, I misspelled the name of this class. Yeah, I'm not quite sure how to handle this without putting mesh data directly into the mesh class. Okay, so maybe the mesh class itself should not actually own the data, only hold a reference to it. That would allow us to store the mesh data inside the OpenGL backend. And then we can simply handle this by the lifetime of the OpenGL backend. Okay, but we can't put this directly into a vector because then they would change its address. So we need to actually store these as unique pointers. That's kind of awkward because it's going to just cause a lot of memory allocation. But maybe we can figure out a better way to store that later. Okay, so that means we can just create unique pointer in this function, populate it with the std make unique function. And then it allows us to store the mesh data using the lifetime of the OpenGL backend. Okay, and then once we have the mesh, we need to actually store the render data pointer in it, which points at the mesh data object. So mesh dot. No, this can't be const, because it is going to modify the mesh. Okay, so we have our mesh here populated with the vertex data. We have our backend. Now we can actually load the mesh data into the backend. I just realized I need to change the capitalization on this function. Okay, so right now all the function is doing is calling gl gen buffers. We need to actually call the gen buffers and then load the data into it. So we're going to use gl bind buffers to do that. Okay, so we call gen buffers, load it into the VBO, and then we bind the buffer to GL array buffer. Then we can actually load the data into it. And the Vertex data stores the local data, but we need to actually retrieve the local data now. So get local data. And then also the local data size. And then we can call the get local data size. And get local data, and that loads the data into the buffer. So we create the buffer, we bind it to the array buffer global state, and then we load the data into the buffer. And with OpenGL, there's no real way of knowing that we've done this correctly. Oh, I did not actually define these functions. And we need to add a constructor here to initialize this pointer to null. Okay, so that runs correctly. OpenGL does not give feedback on whether or not that's doing anything useful. I do have this program on my computer called RenderDoc, which can debug graphical applications. Oh, you know what? I can't actually do this until I start rendering frames. So our render doc is actually not helpful right now. Yeah, so the next step after loading the vertex data is that we need to load the shader, which means compiling the shader, then compiling the program, setting the vertex data attributes, and then we can finally draw it. Okay, so the vertex array object, we should probably store this alongside the vertex data. So we're going to skip shaders for now and just go to the vertex array object. So I'm pretty sure we only need one vertex array object for the whole mesh. So for the vertex data, we call gen buffers on each vertex data stream, but we only need to call vertex arrays once for the whole mesh. Oh, this goes before the vertex buffers. And then for each vertex buffer, we need to start calling these GL vertex attribute pointers. Yeah, this is what binds the vertex buffer object to the vertex array object. A vertex array object just holds multiple vertex buffers. So why is that not highlighted? Okay, I don't remember what these arguments do. We have index, size, type, normalized, stride, and pointer. And I know pointer is just a dummy argument. It's not used anymore, so that's always set to 0. And these functions or these arguments are set correctly, but I want to generalize it so that it works with any definition of get vertex data or any definition of the vertex data stream. So we have the vertex formats that we are going to support right here. And what's defined in that OpenGL call is equivalent to float32 vec3. So we need to define a function that takes all of these, or it defines like a switch statement on all of those values. And that is the case that we're currently supporting. We can add cases there in the future, but now we can just call this function and it'll work correctly. Vertex data. Oh, we need to expose the type and mesh data type of this vertex data stream. Okay, so we create the vertex array object. We bind the vertex buffers here. We set the vertex attribute pointer and enable the vertex array. And then we store that in the mesh. Okay, so it functions without crashing, but I still don't know if I'm calling these OpenGL functions correctly. I am actually more experienced writing Vulkan, and Vulkan has very nice validation layers compared to OpenGL, which has no validation layers, or at least none that I know how to activate. Okay, so now we need to actually add a shader so that we can render something. Actually, before that, let's change this to SDL poll event. Instead of just waiting for events, this will actually run a simple game loop. I don't remember the exact syntax for calling this. I think you need to call event loop, or you need to call poll event in a loop. Yeah, so you just call while poll event inside of the main while loop. And I think once we have the actual loop running, we just call window swap buffers. That will run a OpenGL loop. Okay, so it's probably running as fast as possible. It's not actually responding to the mouse input anymore, and that's not a good sign. Oh, I put that inside of the second while loop. I need to put it outside the while loop. Okay, one thing I want to do is enable VSync on the window so that it's not running as fast as possible, because right now it's probably running at several thousand FPS because it's doing absolutely nothing. So I need to enable VSync on the window. I need to add support for VSync. Okay, so it's using a lot less CPU power, so I think it is actually using VSync right now. But it's kind of weird how it's not actually hitting any of these events. Oh, it's only breaking outside of the inner while loop, that's why. Okay, there we go. So you need to break out of 2 while loops in order to exit the main loop. And let's go ahead and push that to Git. And now I wonder if RenderDoc actually does anything here. Okay, so render doc is actually touching the executable and doing something, but it's not in OpenGL 3.2 context. Okay, I see. So I'm not doing this correctly. Uh, okay, yeah, so I need to add these OpenGL or SDO calls to set the GL context, which okay, so one thing that I violated already is that I'm not, or that this has uh, GL code in the window code. So that means this is not exactly generalizable to non-OpenGL context, but I think that's okay. Well, it's okay for right now, but I think that's also okay for OpenGL ES. Here we go. So this is actually capturing OpenGL. Core profile not explicitly requested. Compatibility profile is not supported. Okay, so it's running in the compatibility profile. Okay, we can actually see our calls here in render doc. And I don't know if I can make this larger or anything. So I don't know if you can actually see this on stream, but this render doc event is calling bind vertex array, bind buffer, buffer data, vertex attribute pointer. So these are all the OpenGL calls we're making. So it is being submitted to the graphics driver correctly. Oh, I just realized that we're not adding this this folder to Git. That's kind of annoying. That means all my Git commits are messed up now. Okay, so we are loading the data correctly onto OpenGL. Now we just need to actually load shaders. Oh, and by the way, I don't know why this is being put into the wrong folder here. I wanted the model viewer executable to be placed inside here, but it's not for some reason. So again, I'm going to do a little bit of a CMake debugging to see where or why it's being placed into this folder. And the base Linux air combat still works. Okay, that moved it to the correct directory. So now that we're actually in the correct directory, we can start adding shader files that are copied into the build alongside the executable. So now when we build this, we have data, shaders, and our test.vertex file. So we can start actually writing the vertex shader here. Which the very first thing we're going to do is just copy from whatever was included, or whatever is described in learn OpenGL, which is this vertex shader. That's just about the simplest vertex shader you can write. Oh, this is version 3. Hold on. I actually want to open this in OpenGL version 3.3. Okay, then our OpenGL backend, we need to add a way to load shader objects and shader programs, which will be eventually stored inside the material class, or references to the programs will be stored inside the material class. Then that can be used by the model class to draw a model. But for right now, we just need to load the shader itself. The way a shader is loaded into OpenGL, you create the ID for the shader using create shader, set the source, and then you compile it. You get compilation errors, which you can handle with this function here. And then you get the fragment shader. And then once you have both the fragment and vertex shader, you can create the program, which contains both of these shaders. Then you can just include them like that. Yeah, so the shaders only need to exist temporarily. They need to exist long enough for the GL use program to use them. Okay, so to add that, I think we just need to add a class to their OpenGL backend. OpenGL shader. This is basically just going to match the usage of the shader object directly. Okay, so it's going to have the constructor and the destructor, which will destroy the shader once we're done loading it into the program. Oh, okay, so we need to actually define which type of shader we're doing. That'll probably be in the constructor as well. I'm going to include multiple overloads here just as a nicety. Okay, so this actually doesn't need size, so I guess it needs to be a null terminated string. Oh, you can specify the length right there. Okay. So we're only loading one, so this is going to be an array of size 1, passing a single data. We need to store this as a int 32 here. And we may as well set that to the correct data type there. Okay, so that should load the source and then compile it, and then we have an actual shader object that we can load into a program. Lord Zealous says, "Oh wow, I didn't realize there'd be another stream so soon." Yeah, I had to I don't know, hit a stopping point yesterday, and now once I finish that out, I figured I may as well continue today because I had some more ideas that I wanted to implement. Uh, as for the future, I don't know if there's actually going to be like regular streaming later on, but I do plan on streaming this project at least as long as I have time. There may be another stream this weekend as well. But okay, back to this shader loading. This should work as long as we have the source code in string format. So we can actually start loading it into the main function here. Oh, I just realized I need to change the name of the load mesh function here as well. Okay, so that should allow us to create the vertex shader. Then we need another one for the fragment shader. And once we have both of these, we need to actually load the data file, or the source code file. So I have the test.vertex, I also need test.fragment. And we can get the fragment shader source code, again from learn OpenGL. And that's being copied over correctly to the runtime folder. So that means that we should be able to load this into the main function pretty easily. means from the main function, we need to actually load the file. I don't actually need to load this as a string. I can just load directly from the file data. Okay, I should actually put this into its own function. Okay, so this load shader function takes the file path and the shader type, it creates a shader, loads the file into this buffer, and then it loads the source into the shader. And then we need to actually return the shader. So that should allow us to call the load shader function right here with the appropriate file path. Okay. And I have no feedback if this actually works at all. Okay, so we're getting a runtime error here. I think it's failing to load this file. So here's the path where it's executing. Oh, I forgot the shaders folder. And also I need to remove this. I need to use the path right there. And there's still an error. I really hope it's not trying to load and run this executable file. Okay, so the file size being returned by the file is invalid, so that kind of hints that we're loading this file incorrectly. I think I need another flag on this. I really don't like the IO stream or the F stream interface here. Okay, so apparently the error is just opening the file in C++. Okay, that's very annoying. Yeah, so it's not even setting error no. I don't know why the C++ file interface is so bad. Also, is it because I'm using an F stream, not an IF stream? Oh, that worked perfectly fine. Okay, yeah, so we had to use IF stream instead of F stream. There was absolutely no error message that gave a hint towards that. But it's running fine now. Okay, so that gives us OpenGL shaders that we can then combine into an OpenGL program. Okay, so this program class should be pretty simple. In fact, it pretty much just mirrors the OpenGL API itself. I don't really want to write anything more complex than that. Okay, so we need to expose the shader ID on the shader class. Why is this green? I have no idea. Okay, so since these shaders can be destroyed, we can actually put this inside of a scope that will allow the shaders to be destroyed right after linking the program. Okay, we got some kind of error message here, which I did not anticipate. I didn't write any error code, so I'm not sure what's actually causing that. Error 1281. Okay, it's really weird that it printed that to the standard output, or standard error, even though I didn't tell it to. But something is being incorrectly created here. Wait, so the vertex shader has shader ID 2. The fragment shader also has shader ID 2. Okay, something strange is happening there. So the path is test.vertex. Type is whatever, that's vertex shader. The buffer contains the vertex source code. And that's loading into the shader correctly. And this one is test.fragment. It's the fragment shader. But somehow this is returning the wrong value, or it's returning the same value for the shader IDs. Okay, I find that really strange that it's producing the same value twice. Wait, did I call compile shader? Yeah, I did. Okay, that's bizarre. It really should be two separate shader values, or two separate values for shader ID. Maybe I need to actually check if there's a compilation error. Nope, there's no error in loading the shader or compiling the shader. We only get the error when we try to attach it and when we try to delete the shaders later. 1281. Okay, every result here is about Minecraft. That's not helpful. Okay, I don't know why these shaders have the same ID at runtime. Okay, this is bizarre. I have no idea why that's not working. Calling all of these values correctly, but I don't see why we're not calling the shader values correctly. I can't find a single explanation for why these shaders have the same ID. Hey Vosgary's been loving your videos. I'm a flight combat sim nerd and software engineer too, so this stuff really hits a sweet spot for me. Oh yeah, I uh Yeah, I'm a software engineer in my day job, and I'm actually starting a job that's very similar to a flight sim, which I can't talk much about, but I'm pretty excited for that because this is basically what I want. It's like combining my hobbies and what I want to do. So yeah, I would consider myself a flight sim nerd too. I'm glad you enjoy the streams. And if you have any idea how to use OpenGL, that would be helpful. So 35633. The next one is 35632. Which are just these defined values. That doesn't help. M shader ID is 2. Also, M shader ID is 2. So I must be doing something incorrectly here because I'm not getting valid shaders. Okay, I cannot figure out this bug. These, these shader IDs should not be the same value, but both of them are set to 2 for some reason. Okay, I cannot figure out this function. There must be something wrong that I'm doing with OpenGL, but I'm getting no kind of feedback. And of course, there's no validation layers, so I can't even. Or, okay, there's these error messages printing in the console, but that's not very helpful. Would it be worth trying it in an isolated standalone project? That's kind of what I'm doing right now. This is a very simple project. This is about as simple as I can make it, so I can't isolate it any more than it already is. Okay, so there maybe something is calling GL delete shader in between calls to here. Oh, you know what? I didn't write a move constructor here, so it's possible that this data is being destroyed every single time it changes scope. So we need to set this to 0, which is like the default value. And then we need to write a move constructor here. Yeah, that was the problem. So it was being destroyed inside this function when it gets returned. It was not being moved properly. Or rather, it was being moved, but that just means copying the handle. So when the destructor runs, it was destroying the handle but then copying it to another location. So that solved the problem. I was destroying it and then continuing to use it. I need to declare this no accept. Okay, anyways, so that allows us to load the shaders and then load the program, and then we can use the program. I should actually put this inside the main loop. Then for our OpenGL mesh, we should be able to bind this object. Okay, I think I need to actually define this a little more vigorously as well. And I need to also add move constructors for basically all of these OpenGL objects. Yeah, okay, so for the destructor of OpenGL Mesh, we just need to delete the buffers and delete the vertex array object. And again, we need to set these values to 0 whenever we move construct this object. Well, actually for the vertex array, which is a vector, we just need to move the vector. Vertex IDs. And then we can write the bind function, which allows us to bind all the vertex buffers. So the only thing we need to do is bind the vertex array. Oh, I need to write the move constructor for this class as well. So we have the shader program, which is we're calling GLU's program, and the mesh that we're calling. Oh, we need to. Yeah, the actual mesh object that I'm holding right now is just the engine mesh type. I need to figure out a way to expose this, even just temporarily. Eventually, I want to put it through here so we have some way to render a mesh and a shader. But just as a temporary measure for now, we're just going to go directly through the get render data pointer. And the final geo call is geo draw arrays, triangles, 3, which is the number of vertices we're drawing. That should actually draw something to the screen. Yes, it does. The position I define these vertices in is kind of strange. But we are now drawing something to the screen. So the position 0, 0, 0, 0, 1, 0, and 1, 0, 1. I really don't know how that corresponds with the data that's on the screen, but 0, 0 should be in the very center of the screen. So I didn't actually look too closely at the fragment shader or the vertex shader, which might be changing one of these. So this is just directly reading the position XYZ. And the fragment shader is just coloring it. That should actually put it in somewhat of a decent position. But I don't know, we can test it with this value they're using in this Learn OpenGL tutorial. Oh yeah, see, it tells us what the coordinates that we're drawing to the screen are. So 0, 0 should be in the center, 0, 1, and 1, 0 should be on the edges of the screen. That's not actually what I see when I run the program. So it's possible that something else is causing our program to behave strangely. Okay, that might be the problem. I'm setting width to 1280 and height to 1280, which is not the correct size of the window. So that means I'm implementing this function incorrectly. Yeah. So 1280 by 720, that should be correct. And there we go. There's the triangle rendered to the screen. So I think that's a good stopping point for the day. We have a single triangle rendered to the screen using OpenGL. And later streams are going to add actual model loading so that we can eventually load all of the data objects that are provided with Linux Air Combat. So all of these model files, I want to write the model viewer to eventually just load and be able to view all of these without actually running the game itself. And then long term, replace the game's rendering engine with the modern OpenGL code. But like I said, this is a good stopping point for today. Thank you for joining. And I mean, however you saw this, if you saw it through YouTube notifications or Twitter, those are the two main methods I will use to announce future streams. So if you want to join, follow the Twitter, follow the YouTube, and hope you catch the next one. Thank you. Bye.